A one-dimensional motion physics problem from the Joy of Physics is solved using the tried and true technique described in the introductory video in this series.
Here's a one-dimensional motion physics problem. It says that there's an airplane touching down at the extreme end of a runway. So then, what's the first thing we always have to do in any kind of a problem like this? Well, we got to read it. So that's why it's up on top here, so you can see it. And then that way you can understand the English of it. So there's an airplane landing on a runway. Okay, so now we have a mental picture. Well, what's the next thing to do? Draw a real picture. So we're going to draw the runway. Here's the runway. One-dimensional motion. So where's the one dimension? What's the runway? That's it. Does that look like a runway to you? You got to use your imagination. Okay, the runway is also known as the x-axis in the way we set things up to solve physics problems. So the airplane is going to land right on the x-axis. How convenient is that? Terrific. So here's the airplane. It's going to land, and it looks like this. And it starts out landing, going pretty fast, right? And then at the end of the landing run, here's the airplane again. And now it has stopped. Great, so now we at least have a picture. This is a V, and actually it's the velocity at zero, because we're going to call our zero of the x-axis right here. This is the origin, and so then it's going to travel a distance along the x-axis, x, until it finally reaches a stop at the other end of the runway. Great. Okay, so now we have a picture. Does this help satisfy your mind's curiosity about what the thing looks like? Hopefully, that's the game. So now what? Now we need physics principles. So where do the physics principles come from? They come from the book. The book has a bunch of them. There's some on pages 30 and 31. And these physics principles are often called the big three. And the big three is a set of equations that describe one-dimensional motion. They say x equals x0 plus v0t plus 1/2 at squared. And v is equal to v0 plus at. And then the third equation is one found by eliminating t from these two. And it is v squared equals v0 squared plus 2a times, whoops, it's not much of an a, 2a times x minus x0. You're going to watch the drawing because you're going to look at these things later, right? 2a, right, times x minus x0. Okay, those are the big three. Great. So now what? Well, now what we have to do is identify what it is that we know and what it is that we're trying to find out. So the problem tells us what x is. In fact, let's look right at the equations. X we know. The problem gives us that. It's 1,500 meters. X0, what's that? Well, that's x at the start of the problem. So where's the start of the problem? It's right here. We've decided that we're going to set up our x-axis like this, and this is time 0. So x0 is what is the value of x when time is 0, and that's 0. So that's nothing. We know that. v0, that's actually what we want to know. A part says, what is the plane's velocity as it begins to land? That's v0. So this is an unknown. Then t, that's the time it takes to make the landing run. Do we know that? No, that's the B part of the problem. So that's also an unknown. Do we know A? Yeah, it says that it decelerates at 3 meters per second squared. Okay, so we know that. T is also an unknown. Right. So now can we use this equation to solve for V0, which is the first thing we want to know? Well, we have a fundamental problem here. We have V0 and T as being unknowns, and we have, so therefore, 2 unknowns and only 1 equation. Doesn't work mathematically, so we can't use that. Sorry. How about the second equation? V, that's the velocity at the end of this time interval. Do we know what that is? Yeah, we know that, not by equation, but we know that because of a word. The word says it rolls to a stop, and stop means V is equal to 0, right? V0, do we know that? No, that's what we want to know. A, do we know that? Yes, given in the problem. T, do we know that? No, we don't know it. We have the same problem that we had in A, and that is we have 2 unknowns, V0 and T, and only 1 equation. That isn't going to help us either. Hopefully the third one will. So let's see what the third one says. V, that again is 0. V0, that's our unknown. A, that's given. X is given. And x0 is also 0. Now we're in business. because now we have an equation that has one unknown and the rest knowns. Great. So we're solving part A, and we'll just take this equation up there. That's a 0 equals v0 squared plus 2ax. Boy, the a's are troublesome today. Wow. Okay, so then, great. We should be able to solve this. And v0 is what we're after, so we can say v0 equals the square root of minus 2ax. Right, square root of minus 2x, fine. So now all we have to do is put in what a and x are, and we'll be at the solution of the problem. Square root of minus 2 times a. And a is given in the problem. It says it decelerates at 3 meters per second squared. Can we just blithely put down 3 meters per second squared here? Not quite, because it decelerates. What does decelerate mean? It means it slows down. So a deceleration is actually a negative acceleration. So we have to put a minus here, 3 meters per second squared. X, it says, is 1,500 meters. So that completes this. So now, oh, isn't it nice? The minus 2 and the minus 3 gives you a positive. Great, we'd like to have the square root of a positive. We hate to have square roots of negative numbers. They're called imaginary. Mathematics don't like those. So, okay, what is that altogether? Well, I worked it out. Numerically, what it is 94.9 meters per second. The 94.9 is the number. How does this get to be a unit of meters per second? Meters squared per second squared inside the square root. Take the square root of that. Does square root apply to units too? Sure. So 94.9 meters per second, that's our answer. Have to apply our test of reasonability. Does this seem reasonable? Well, I converted it to miles per hour for you, and it turns out that this is 212 about miles per hour. Does that sound about right? Yeah, well, the big jets land at about probably that, or maybe more. So that could be okay. So we'll take that. Okay, part B. Part B says, find out the time needed to complete this landing. So how do we do that? We're going to go back to our equations. So then, we already used number 3. Do you want to use one of these two? Well, we can use this one, because now that we know the V0, that'll have only one unknown, but it has it squared and linearly to the first power. So do you like equations that have squares in them? What do they call those? Quadratics, right? Do you like quadratics? Not so much, especially if you can find it easier. Look at this one. This one has V0, which we now know, and then T, this only has one unknown. So we're going to use this equation right here. And we'll transpose it and say 0 equals V0 plus AT. Great. Now we've transposed that equation. And so we'll solve it now for T, because that's our unknown. T equals minus V0 over A. Okay. Now what do we have to do? Put in V0 and A. So then here's the V0. There's a minus in front of the whole thing. 94.9 meters per second divided by A, which is minus 3 meters per second squared. And so altogether, that turns out to be 31.6 seconds. What happened to the minuses? Well, minus divided by minus, it's just plus. And so that's good, 94. So 31 seconds. Let's apply our test of reasonability. Does that seem reasonable? Does it take 31.6 seconds to land a big airplane? You'd think, let's see, how's your experience on that? Well, let me put it this way. Suppose we had made a mathematical error and it turned out to be 0.316 seconds. We would have said, have you landed an airplane in 0.3 seconds? No, there's no way. TSA would never let you get away with that. Okay, so this looks like we may be on the track of success. There'll be a few other physics problems to follow, so make sure you use this kind of technique and you'll get there.
Oh!